My name is Sudipta, and this is my Physics 2211 Falling Slinky lab report. The purpose of this lab is to observe and model the motion of a stretched slinky dropped from static equilibrium. We will then compare a computational model created in GlowScript to the observed motion and explain any differences found. We will be applying Newton's second law and other physics principles to predict the slinky's motion at different times. We will be exploring Newton's second law, which is also known as the momentum principle, which is just F net equals dp by dt. We will also be using the velocity update formula, which iteratively updates the velocity. We'll be using the force of gravity, which is just F equals negative mg, and g is just the gravitational constant, and the force of drag, in which b is the drag constant, and then F net is calculated by summing the individual forces. I use the Tracker app to record the change in position of the slinky per frame, and on the right there's the graph modeling the y position of the slinky versus time. I use GlowScript to produce a computational model of the slinky's motion. I inputted the mass of the slinky, which was just 0.25, and then the initial position of the slinky and the initial velocity of the slinky. It starts at rest, so it's just 0. And then I inputted the gravitational constant, 9.8, and the proportionality constant for drag, which I found through trial and error. In the first while loop, W is the net force due to gravity, and Ft is the force due to tension. I inputted the velocity update and position update formulas to calculate the velocity and position iteratively. I set the time to keep advancing. In the second while loop, we account for drag force. We calculate the net force by summing the force due to gravity and drag with the proportionality constant. I still use the velocity update and position update formulas to iteratively calculate the slinky position and velocity with each time step. This is a comparison of the experimental data and the computational data, which shows some discrepancy as time advances. Results, and what does this mean? Does the bottom of the slinky stay stationary just like in the video? Yes, the bottom of the slinky stays stationary at the same y position until the top pushes down. When the bottom is stationary, the gravitational force and tension force are equal in magnitude and opposite in direction, so they cancel out, and this yields a net force of 0. When the bottom starts moving, both drag and gravity act on the slinky. Discrepancies between the observed and predicted models could be due to the additional forces not taken into account, or even human error in determining the point of mass in the tracker. Thank you.